All right, we are now recording. Start the slideshow from the current slide. First thing I want to know, any questions on anything we've covered so far? None? Okay. So, this is a little bit of a review. This is where we left off last time. Tyrell is here. Okay. A little bit of review, what we were saying before. To decompose a function, a composite function, look for the innermost part of that function and the outermost part. In the previous one that we were doing, let me plop that up there again, this one, okay, look at h of x equal to this, okay? This is the innermost part, there's the outermost part. So the innermost function, your g of x, is the 3x minus 5. The outermost function is x cubed. Okay? So, look for the inner and outer, and they've repeated it again. Okay. Now, what they did do was skip the example 7. And again, some of the people who requested it are not here, but they'll have to listen to the YouTube video to catch it. Okay? Here's a function, h of x. Okay? So h of x is equal to 1 over x minus 2 squared. Now, it says write this h of x as a composite of two functions. Now, lines here. This one, there are several different ways you can go. There's not just one fixed way. There's several different ways. In fact, you could decompose this into 3 functions, which is a perfectly legitimate thing to do. But it says do it in 2. Jeremy's here. There you are. All right. Now, you give me an idea what you think might be a way to go. We need to decompose it, and it says into 2 functions. So then what we'll need is an f of x, and we'll need a g of x. And traditionally, we usually use g of x as the innermost. That's where we should start. What do you think the g of x should be? And really, there's 2 choices. X minus 2 is an excellent choice. X minus 2. What would then be the f of x? Okay. Are you doing it in 3 pieces or just 2? 1 over x squared. Got it. Okay. That would be the decomposition of this into 2 functions. Another would be g of x would be 1 minus x squared. X minus 2 squared. And then f of x would be 1 over x. That would work. Or you could split it into 3, have an h of x be x minus 2. No, I'm sorry. What would it be? I of x, okay. I of x would be x minus 2. G of x would be x squared. And f of x 1 over x. You could do it many, many ways to do it. Okay? But you always have to have something of that innermost function to be your first, then work your way out. Kind of like peeling an onion in reverse. Okay, you start in the inner part and work our way out. All right. Any question on that? And by the way, yeah, they did the g of x to be x minus 2. I was going to see that. And then the f of x would be 1 over x squared. And by the way, I hope you're familiar with this. Can you give me another way to write the f of x rather than 1 over x squared? Do you know of a hint? Second? Yes, x to the negative 2. Okay? That is another way to write 1 over x squared. And the book writes it both ways. It doesn't look as much like this, so I wouldn't suggest it in this one, but if you like it that way. for those of you, and I hope several of you will continue and pursue into calculus, if you do, you far prefer integrating forms like that than forms like that. So that's one reason to go that way. Any questions on that? All right. Again, some of the people who asked for it aren't here to hear it, but hopefully they'll pick it up on the YouTube video. So now let's look at an application. All right. I always think of Thanksgiving dinner when we do this application. Probably isn't a good thing to think of Thanksgiving dinner. But the number N of bacteria in a refrigerated food is given by N of T. Now, this T is temperature. N is number of bacteria as a function of the temperature. The way they've worded this is strange. Okay, I'll explain it in a minute. Is equal to 20T squared, so again, this is temperature, minus 80T plus 500. Okay? But this is only good from T 2 to 14. Okay? And T is the temperature of the food in degrees Celsius. So this is just above freezing. That would be about 35, 36 degrees Fahrenheit. Okay, just a little bit above freezing. Going up to 14, which would be considerably below room temperature. Now, here's what they're saying. This isn't refrigerated food anymore. This is food that you've taken out of the refrigerator. Because in the refrigerator, usually you're around 35, 36 degrees Fahrenheit, which is around 2 degrees Celsius. You don't want things freezing, but you want them kept cool, okay? And that's why they have this here. So you pull something out of the fridge, and then as it increases in temperature, here's what your bacteria count will be, okay? Now, T is the temperature of the food in degrees Celsius, because you see, then your food will be warming up, getting close to room temperature. When the food is removed from the refrigeration, the temperature of the food then is given by this, okay? T of T, now this T is temperature, that T is time. The temperature as a function of time is 4T plus 2. Now this is only good for time 0 to 3 hours. T is the time in hours. So when you pull it out of the fridge, the temperature starts rising at that rate. Now, here's the interesting part. See how it meshes together. When your time is 0, which is when you first bring it out of the fridge, what is your temperature? When little t is 0, what's your temperature? 2 degrees, and that's what it was when you pulled it out of the fridge. See, this problem sort of makes sense. Okay. So that's time in hours, little t, capital T temperature. Degrees Celsius, not Fahrenheit. Find the composition N composed with T, that's temperature T, of little t time, and interpret its meaning in the context of this problem. So let's do this first part. What do we mean by N composed with T? That means N of capital T of little t, right? Okay, now, tell me what to write for that. What do we plug in first? The little t, the capital T of little t. The N of, you tell me what to write, 4T plus 2. Okay? Now, let's plug that in. The capital N function does what? It starts with a 20, okay, and then it takes what's in the parentheses, which here is 4T plus 2, and squares it, subtracts 80 times it, the 4T plus 2, and then adds 500. All right. Now, we got a little bit of work to do, but that's what's going on. And frankly, I know y'all may think this is a weird looking problem. To me, this makes a lot more sense than having the variable for this one to be x and that one to be x. You don't know what x is. Here, this t is temperature, that t, time, that t is temperature, that's number. Everything sort of makes sense. So now you don't have x's in different places and meaning different things. This makes, to me, a lot more sense. Okay? What have we got to do first in this expression? Okay, we've got to square first. So leave the 20 alone. That's supposed to be an equal sign, but my screen collapsed on me and it didn't come across too well. So let's go back and make that equal sign a little bit clearer. Okay, let's square that 4t plus 2. What would that be? 16t squared plus 16t. Okay, remember the rule for doing that? If you need to, go off to the side and do your FOILing. You know, 4t plus 2 times 4t plus 2. But if you're trying to use the rule, square the first, 16t squared, twice the product of the 2. The product is 8t, twice that would be 16t. And then the last one is plus 4. Okay? And then we can go on and do this one if you want to. What's that going to be? Minus 320t, right? Okay. Next. And, minus 160 plus 500. All right. Let's clear the parentheses here. Sorry, don't have a lot of room on this slide. What would that be? Big number. What is it? 20 times 16? 320 t squared plus 320 t plus 80 minus 320 t. That's sort of nice, isn't it? Minus 160 plus 500. Okay? What's one thing you see you can do right off the top? 320t, add and subtract, adds a 0. Next thing, combine your like terms. Now I'm going to combine them this way. The positives are 580, and then you're subtracting 160 from that. That gives you 420. Okay? So this is equal to 320 t squared plus 420. That's all that's left? I believe so. So that is your n as function of temperature as a function of time. So it winds up being n as a function of time. So we found it. Okay, there it is. Okay, that's your form here. Interpret the meaning of that. What does that mean? What does this function up here mean? The n stand for? As a function of? Yeah, this is now in time. You've got the temperature out of the picture. So, to me, that's why I think of Thanksgiving. Always after the big meal on Thanksgiving, everything goes into the fridge, right? And then that evening, if you eat Thanksgiving, here it comes out of the fridge. Help yourself, I'm not going to do any more cooking. Have you ever heard that? Have you ever said that? Yeah, okay, never mind. Okay, so it sits out there. Oh, I'm not all that hungry. So it sits there and sits there. And what does this mean? The longer it sits, when you first bring it out of the fridge at 2 degrees Celsius, how many bacteria are living in there? T equals 0, little t 0, 420. Not too bad. Our stomach can handle that, can it, most of the time? Okay? But how many hours are you going to leave it sitting there? You choose. What's typical? Before you say, oh, someone put the food up? Give me an hour. 2 hours. Okay? 2 squared is times 320. Will be a pretty big number, right? Plus 420. Think of how many little bugs you're eating now. Okay. Okay. Yeah. Maybe I shouldn't think that concept. Okay. Now, here's the next part of the question. Find the time when the bacteria count reaches 2,000. How are we going to do that? Say again? Okay, your N is your 2,000. That's the number of bacteria, 2,000. So the N is going to be 2,000, and then you solve that equation. So let's plug it in, plug it in. Let me come down here and do it. Okay, is that all right? 2,000 is equal to 320 t squared plus 420. That's what we're trying to solve. Find the time. My wife's always telling me that. Well, you just find the time to do it. No, she doesn't. Okay. Now, what would be your approach to answering that question? Okay. You could do that. Yeah. That's a decent way to go. So let's do that. Subtract 420 from both sides. And that would give you, I'll write it over here, 1,580. Is that right? Okay. Is equal to 320 t squared. Okay. Now what? Divide both sides by 320. Okay. Gets rid of that. That got rid of that. So someone with a calculator. Okay, that's about 4.937. 937. But that's t squared. Okay. I don't really care what the square of t is. I want to know time. So how do we get that? Take the square root of 4.937. And what does that give you? 2 point. Someone do it already? 2.3 or so, something like that. 2.32? 2.22 hours. Okay, I don't usually measure my hours in 2.2s, so how could I get that to make a little more sense to me? I can understand the 2-point part, that's 2 hours. 20.22 hours would be 0.22 of, how many minutes in an hour? Of 60. That would be a 0, 2, right? 2 decimal places. About 13 minutes. About 2 hours and 13 minutes. If I did it right. Okay? Well, we're going to see what they did. Let me just look and see. Yeah, they said 2.2. Yeah. Okay. All right. Okay with this? Let's see how they did it. Well, they started off N of T, just like y'all did. The composition of N with T of T, number of bacteria with temperature as a function of time, is, the definition is N of T of T, just like you said. Now we take the T of T, the temperature as a function of time function, and put it in for the N of T. They did it in 2 steps, okay? They did it in 1 step, what we did in 2. 20 times 4t plus 2 squared minus 80 times 4t plus 2 plus 500. I think the skip steps here might be a little premature, but it's okay if you understand it. And then they expanded this and did that just like we did. And that came out 320t squared plus 320t plus 80 minus 320t minus 161 plus 500, exactly like we did, and solve that these two disappear, plus and minus, those add to 0. The others combine to be 420. I think that's what we got. And then the interpretation of that, the composite function here represents, we started off with number of bacteria as a function of temperature, then we had a inner function of temperature as a function of time. When you compose those, you wind up with number of bacteria as a function of time. And that's exactly what we did. The composite function N composed with T, number of bacteria composed with the temperature as a function of little t time, represents the number of bacteria in the food as a function of the amount of time that the food has been out of refrigeration. And that's what we saw. Okay? So the bacterial count reaches 2,000 when that N of T, little t, is equal to 2,000. The number of bacteria is 2,000. And they didn't show how they got it. They just said it's about 2.2 hours. And rounded that way, that would be 2 hours and 12 minutes. We said 2:13 because we used the extra decimal point. That's fine. Okay? The extra minute's not going to add that many bacteria. Okay. So you had said 2 hours, so we were probably down around 1,800 or so at 2 hours. We never did figure that out, did we? All right, any questions on that? Does it make sense? Okay. Now, let me just go back to our original problem. I hate that all that's in the way. Here we're only letting the temperature get up to 14 degrees Celsius. And the reason for that is we're only allowing it to be out 3 hours. And I bet you, let's just do it, let's plug in 3 here. 4 times 3 plus 2, 14. So you see, it's a well-posed problem. They put it all together. Now, I'm wondering why they cut it at 3 or at 14 degrees. I have a feeling those little boogers start exploding like crazy, you know. They probably grow somewhat slowly to begin with, and then after a while, they're really taking off. So, yeah, that's my guess. I don't know. But, okay, this is an example of an explicit domains. This isn't good for t equals 0. Okay? That's taken out of the freezer. Okay? This is out of the fridge. This is only works for t equals 2 to 14. This is only good for 0 to 3 hours. After that, it's probably going to be a far bigger increase, or maybe a smaller increase. That's where it's about linear. Okay? So both of those are what we call explicit domains. That function works for all real numbers. We're not interested in all real numbers, just positive. Oh, and that leads me to one other thing. And this is the thing about the way, was it on this page or the next page? Maybe it was the next page. Nope. Somewhere here, yeah, down here. Really, when we took the square root here, we should have done plus or minus 2 hours, 2.22 hours. Well, anytime you take the square root. But remember, this t is not good for negative numbers. That's why we only went with the t, with the positive 2.22 hours. Yes, and that's the reason, because you can't think. It wasn't growing bacteria back when it was still in the refrigerator. That would make no sense physically. That's why this is here, and that's why we didn't even consider it. I meant to say it at the time, but I forgot to. Good deal. Any other comments, questions, or whatever? There is a checkpoint there. If that looked like an interesting problem to you, by all means do the checkpoint. And if you have trouble in the checkpoint, the audio-video solution is at larsonprecalculus.com. All right. Good deal. And by the way, oh yeah, I can't remember. I think the checkpoint answers aren't in the back of your book, are they? Okay. I wish they had them there too. Okay, I think we've done all this. Okay, note that when you solve this, here's what it was. I just didn't scroll scroll down the next tick here. Note when you solve the equation, you reject the negative value because it's not in the domain of the composite function. Okay? And that's what we're just talking about. Now, that was probably the best way to work that problem. It's not the only way, this last part. You could have done this. 320 t squared plus 420. Well, subtract that, sorry. Just like we did, leave it on one side of the, I'm sorry. So let me back off here. Let's subtract the 2,000 from both sides, which we already did when we got minus 1,580, wasn't that it, equals 0. And what I would do is simplify by dividing by 10, and then probably divide by 2. That would be 16t squared minus 779, right? I believe that's right. Equals 0. And then you could use the quadratic formula. You don't have to simplify like that, but I just like to simplify. Keep the numbers as easy as possible. And then when you do, you'll get a plus or minus. You throw out the minus. Okay? Or you can do what we just did. Leave that on the other side. Divide 79 by 16. Especially if you didn't have a calculator, that would be an easier calculation made. Any way you do it, it works out. Okay. So, that is the end of 1.8. Let's do the vocabulary. Didn't need to talk much on this one. I only have 2 vocabulary, but there's several blanks. 2 functions, f and g, can be combined by the arithmetic operations of blank, 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 and blank. What's your arithmetic operations? Addition, subtraction, multiplication, and division to create new functions. Number 2, the blank of a function of f with g is f circle g. If I say it, I'll give the answer away. Of x is equal to f of g of x. The composition of the function. Absolutely. Homework exercises. Do number 3 if you haven't already. Any of the odds 5 through 11. Any of the odds 13 to 23. Do 25. Do either 27 or 29 or both. I'm sort of surprised no one's asked me about any of these because some of them are things we haven't really done in class, but if you figured them out, that's great. Either 31 or 33 or both. Any of the odds 35 to 41. Either 43 or 45 or both. That's using the figures there. Any of the odds 47 to 53. And then any of the applied problems, odd numbers, 55 through 61. And again, I would pick ones that either you have the greatest interest in or may be closest to your majors. Okay? Interesting looking one with pets there. Okay? There's exploration that you can also take a look at. 63 is good to think through. 65 is a true-false, good to think through. Then we have some proofs and other things, conjectures. Any of those that you want to take a look at, you can, but don't expect to see many of that nature. But it's good things to think about. All right, any questions on 1.8? Okay, let's move on to 1.9, which is right here. Just a few minutes to go through all this rigmarole again. And is it just me because I'm up here talking so much, or is it getting a little warm in here? You okay? Okay. All right. Let's start from the current slide, and we'll go. All right. Continue with functions in the graphs. Okay. We're now going to talk about inverse functions. what are we talking about with inverse functions? Let's go back, way back, years back. What's one of the first things you learned to do when you started doing math? Addition, yeah. You started adding numbers. And if I remember right, which was so long ago, that was a little bit traumatic because now we're having to remember all these things, memorize some stuff. And then when you thought, I think I finally got it, what did they turn around and do? Subtract. And what does subtraction do? It undid your addition. Okay? And how did you check it? You went back and added the two numbers you had left. Yeah. So actually subtraction is an inverse function of addition, though we didn't call it that back then. And then you say, oh, finally got that done. And then they introduced these timetables. And you had to start doing multiplication. So you did those and did those. Boy, that took a while. And then about the time you thought you finally had this knot, they introduced division, which undid multiplication, right? And multiplication undoes division. So they're inverse functions of each other. And then sometimes much later, probably years later, we finally started raising numbers to powers, right? Squaring numbers, cubing numbers, raising forward. That was a little different, but we were older then, we could handle it. Then they turned around and had us undo that. How did they do that? How do you undo a power? With a root, exactly. Square roots undo squaring, cube roots undo cubing. Yeah, so we had another inverse function. So all the way along, all of mathematics is yin and yang. You do something, you undo it, okay? That's what we're going to be talking about here, but now we're going to do it with functions that have multiple operations in them. So we're going to see how we can do that. So we'll find, and the way the book does it, I really don't care for it, but we'll do it this way. Find the inverse functions informally. In other words, you're guessing, and then you verify that two functions are inverse functions of each other. You make a guess, and you see if they work, okay? Kind of like factoring, sometimes, isn't it? Okay. Then we'll use graphs of functions to determine whether the functions have inverse functions. Because guess what? Not every function has an inverse function. Okay? So we'll use graphs to help determine that. We'll come up with a new test. We've always had the vertical line test to see whether it's a function or not. We're going to come up with a horizontal line test to determine whether the function is one-to-one. Well, here we introduce a brand new thing here. What in the world is a one-to-one function? We'll talk about that and then use the horizontal line test to determine it. And then we're ready to find the inverse functions algebraically, which to me is a lot better than the guessing. Okay? Why do they waste their time on guessing? But to give you insight, you know, and I don't know. Okay. So let's look at inverse functions. What do we mean by it? We know that one way you can express a function is a set of ordered pairs. This would be a discrete function, right? For instance, if f of x is equal to x plus 4. Pretty simple function, right? Now, but let's say our domain, normally we'd say the domain of that would be all real numbers. But let's restrict ourselves to this domain. A is 1, 2, 3, and 4. Okay? So with just these numbers, let's operate with function f. What would it be if you plugged in a 1? 5. Who do we appreciate? No, okay. All right. So we take out of this domain and feed into that range, right? Okay, that function does that for us. It maps these numbers onto those numbers. Okay. Now we can express that function, f of x is equal to x plus 4. Yeah, we did that. Such that here is the set of ordered pairs. 1 maps onto 5, 2 maps onto 6, 3 maps onto 7, 4 maps onto 8. So there's another way to express a function, as an equation or as a set of ordered pairs. Now in this case, you can interchange the first and second coordinates of each of those, and you come up with an inverse function. And what we'll name that inverse function is this. F to the minus 1. Now, when you see a function symbol with a minus 1, that means inverse. That's the inverse function of f. That's what that means. If you see x to the minus 1 or 7 to the minus 1, what does that mean? 1 over x or 1 over 7. That's not what it means for a function. The minus 1 superscript, with a function means inverse. With a number or variable, it means reciprocal. Okay? So don't get those two confused. The slide will talk about that later, but I wanted to bring it up now. Okay? So what we're doing, we're exchanging the two things. So can you write for me what f inverse would be? We may not know the, let me get my pen back. Okay. F inverse of x. We don't know this part yet, but we should know this part. What you reckon those ordered pairs would be? 5, 1, 6, 2. That's pretty tall, okay? 7, 3. That's really tall, okay? Never mind, okay. That's ridiculous. Okay. That would be the inverse function of that function f. Now, we see if we can come up with an equation that will take the first number and produce the second number in every one of those. What can you do to the first number to make it that one? This number to make it that one? This number to make it that one? That number to make it that one? X minus 4. There's your inverse function. X minus 4. And that kind of makes sense, doesn't it? Because subtraction is the inverse of addition. Yeah, that's sort of making sense now. A little bit, maybe. Okay? So, I jumped ahead. The inverse function of f, which is denoted f inverse, okay? It is a function that maps the things from set B, what was the range of f, onto the set A, which was the domain of f. So it just flips everything. And can be written as follows. The f inverse function would then be x minus 4, which you noted, but we got it first by looking at this. The ordered pairs were 5, 1, 6, 2, 7, 3, 8, 4. We already did that. Okay, note that the domain of f is the same as the range of f inverse. The domain of f, that was 1, 2, 3, 4, that's the range of f inverse. And vice versa, what was the range of f, 5, 6, 7, 8, that's the domain of f inverse. Okay? Now, also note that the functions f and f inverse have the effect of undoing each other. I've been using that terminology already. So, what we mean here, this is the mapping way to express a function. Here we have a set of numbers, 1, 2, 3, 4, the x values, which is the domain of this function, f. When f operates on 1, 1 plus 4 becomes 5. 2 plus 4 becomes 6. So you go into the range here. And that's f of x. Okay? That are numbers that you get from plugging these values in to that f. So that's the range of f. But then when you do an inverse function, that becomes the domain of f inverse. It goes back along the reverse route and takes you back to the same x as we begin with. So the domain of f inverse becomes the range of it maps onto the range of f inverse, okay, through the f inverse function, and that winds up being exactly the same as the domain of f. Okay. So one undoes the other. And whichever one you started with, you can get back to the other one the other way. In other words, they have lots of other words here. When you form the composition of f with f inverse, or the composition of f inverse with f, you wind up back where you started with, which is the identity function. Don't you? F of f inverse is x minus 4. F operating on x minus 4, remember f was x plus 4? Okay, so if you operate on this, x minus 4, that would be exactly what they have here. X minus 4 plus 4, and what do you wind up with? X. Okay? Or, if you operate with F inverse on F, F is X plus 4, operate it with F inverse, which is X minus 4, it would be X plus 4 minus 4, and that gives you X. Now remember back a long time ago, at least 2 days, when we said that in general, if you do F composed with G, it's not the same as G composed with F, right? Except for special functions. We just found them. Inverse functions of each other, they are commutative. And not just commutative, they always equal X. Exactly what you started with. Okay? Make sense? Okay. So, let's find the inverse of f of x. Okay? Now, this is one you're just making a wild guess. Hopefully it won't be too wild. What might that be? Say again? Okay, let's try it. Negative 4x. That's all we're doing, trial and error here, right? Now, how do we check to see if that works? We check to see if f of f inverse, see what that's equal, but we also check and see what f inverse of f equals. Okay? You thought you were through with these, didn't you? Okay. How do you do this one? What's your f inverse, or at least your proposed f inverse? Negative 4x. And what does f do? Okay, so there you would have 4 times negative 4x, and that would be negative 16x. Frankly, that doesn't look too promising, but let's do the other one and see if we get the same thing. What's your f of x? 4x. And then, what does it do? Okay, multiply it by negative 4. And guess what? You do get the same answer, but it's not x. Okay, that would be negative 4 of 4x. It is the same answer, but it's not x. It's not the identity function. You had to pick one that would do that, didn't you? Okay. See, our requirement is it's got to equal x. So guess what? Not the inverses of each other. So we need to try another one. That didn't work. So what other inverse function might we try? Okay, say that again. Okay. 1 over 4. Is that what you said? Okay, let me get it. 1 over 4. Okay? Then f of f inverse would be f of 1 over 4. And that would be 4 times 1 over 4, which would be, now x, 1. Okay? That's a little bizarre, but, sorry. Y'all awake yet? Okay, good. Your f inverse of f, that would be 4x, and then, let me erase the rest of this. I was in the middle of erasing when you came up with your proposed solution. Okay. We'll get there maybe. Okay. And f inverse, what is f inverse? Is 1/4. No matter what you put in there, f inverse is 1/4. So f inverse of 4x is, according to what you said here, is 1/4. Okay? So that would be 1/4. And guess what? 1 and 1/4 are not equal. So that's not right. But you're not far off. Anyone want to make one more try? Or we can try as many times as you want. What might be our F inverse? Say that again. Okay, say that again. Yes, there is, and that comes at the end of the section. That's why I don't like doing it this way. But this is supposed to give you insight and feeling for it. No, wrong. Okay. 4 over x. Okay, we could try that. Huh? Okay. Let's flip those. X over 4. Think about this. This one is taking your variable, multiplying it by 4. The inverse function is going to take the number and divide by 4. Remember before? It was x plus, what was it, 4? Yeah, x plus 4, and then we did x minus 4. Here's x times 4, so do x divided by 4. So quit guessing, we'll do that. X over 4. Okay? So f of f inverse would then be f of x over 4, and the f function takes the number 4 and multiplies by what's inside. That would be x over 4, and guess what you get? X. Let's do the inverse of that. F inverse of 4x. I didn't have to erase that. It was always the same. And the inverse function takes what's in the parentheses, 4x, and divides by 4. And what does that give us? X. Ding, 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 ding. We got it. That's it. Okay? Now, I don't like doing it that way. Trial and error, I make too many errors. Okay? I'd rather just cut to the chase, find the easier way to do it, and we will get there. Why they do it this way, I don't know. There's a thing in education theory. You need to have students experiment, you know. Am I being facetious? Probably. Yeah, I am. Let's erase all that. Okay. All right. The function f multiplies each input by 4. To undo this, you need to divide each input by 4. That's what we wound up doing. So your f inverse was, if f of 4x, f inverse would be x divided by 4. Now to check it, you do f of f inverse, that would be f of x over 4, and the f function takes what's in the parentheses and multiplies it by 4 times that, so that would be 4 times x over 4, and sure enough, that becomes x. And doing the other way, f inverse of f of x would be f inverse of 4x, that was your f function, and the f inverse function takes what's in the parentheses, now it's going to be 4x, and divides by 4, and sure enough, that also gives you x. So this is one of those cases where the composition is commutative, and not just commutative, it produces the identity function, x. That's what we're looking for. All right. So here's the definition of the inverse function. If f and g are two functions such that f composed of g or f of g of x always equal x for every x in the domain of g, and g of f of x always produces x for every x in the domain of f. Now notice these two x's aren't quite the same because this has to be in the domain of g, this one has to be in the domain of f. But if that's the case for all x's in those domains, under these conditions, f is said to be the inverse function of g is said to be the inverse function of f. The function g is denoted by f inverse. So f of f inverse is x, and f inverse of f is also x. The domain of f must be equal to the range of f inverse, and the range of f must be equal to the domain of f inverse. Same thing we've been saying all along. So that's your definition of these inverse functions. Now they get around to saying what I said before. Do not be confused by the use of -1 as a superscript to denote the inverse. If this is a function here and you see the -1 superscript, that doesn't mean reciprocal, it means inverse. adds a little bit of confusion to this. With numbers or variables, you also call the reciprocal the multiplicative inverse. So in the sense it is, but only in multiplication. This is talking about any inverse of the function. In this text, whenever f inverse f to the minus 1 is written, it always refers to the inverse function of f and not to the reciprocal of f. Always. If that's a function, the minus 1 superscript means inverse, not reciprocal. If the function g is the inverse of the function f, it must also be true that f is the inverse of g. Remember, they go both ways. Okay? For this reason, you can say that f and g are inverse functions of each other. Another way of saying that, and it's not restricted. Now, they skip example 2. Okay? Let's go back and do example 2. Right here. Well, gotta get my pen back. Okay. Gotta get my pen back. Okay, got it finally. Here's a function. F of x is equal to 5 over x minus 2. The question is, which of the following two functions is an inverse function of f? Okay? Here is g of x is equal to x minus 2 over 5, and h of x is equal to 5 over x plus 2. Okay? Which of those is the inverse of f? How can we tell? What is our test? Second, yes, we look at the composition. So let's start first with f composed with g of x. Okay? What would that be? F, plug in the innermost first, and what would g of x be? X minus 2 over 5. Okay? Now the f function directs you to start with 5 divided by what's in the parentheses, which is this thing, x minus 2 over 5 minus 2. Did I do that right? Okay? Only reason I'm talking too much is we're running out of time. Ooh, we got some work to do here, don't we, folks? 5, yeah, everything, numerator and denominator by 5, because 5 over 5 is 1. You can multiply by 1 anytime you want to. Just multiply this by 5, and multiply both of these by 5. Okay, so this gives you 25 over, here the 5's go out, x minus 2 minus 10, which is 25 over x minus 12. Is there any way that's going to be x? None I can imagine. So I would say g is probably not the inverse. It's not the inverse of f. Okay? Let's try the other one. F of h of x. That's what we're going to try next. And what would that be? F of, what's your h of x? 5 over x plus 2. And what does the f tell you to do? Start with the 5, put it over whatever's in parentheses, 5 over x plus 2 minus 2. Okay, now I put the parentheses there. They really aren't doing me any good, so I'm going to take them back off. I just want to do it to show you that's my x. What's acting like the x here is that thing. Okay, so let's take that off. And what do you notice you can do with that? Okay, not yet. How about this? Plus 2 minus 2 adds to 0. Okay, and now not a bad idea to multiply numerator and denominator by x. Okay, and here we have 5x over, here the x's go out, 5, and guess what that's equal to? X. Have we shown definitively that these are inverses of each other? Nah, we really need to do it the other way too. So I'm going to get rid of the g's because they weren't very helpful at all. Ooh, yeah, okay. And let's do it the other way, just to make sure that we haven't messed something up. Okay? If I was in the Navy, let's try to make it sailor-proof. Never mind, we won't go there. Let's try and see what h of f of x would be. What would that be? Plug in the innermost first. What's your f? 5 over x minus 2. And what does the h function tell you to do? Write down the number 5, divide it by what's in the parentheses, which is 5 over x minus 2, and then add 2 to that. Okay. What would be a suggestion here? X minus 2 sounds like a good idea. Multiply this by x minus 2, this by x minus 2, and this by x minus 2. Multiply numerator and denominator by x minus 2. That is 1. So this in the numerator becomes 5x minus 10. Denominator here, that goes out, and you get 5 plus 2x minus 4, right? Is that what you said? Okay, let's clean that up a little bit. Boy, this is getting messy looking, isn't it? That's 5x minus 10. Well, let's factor that. Why not? Can we? Okay, yeah. Because I'm running out of room, I want to save as many steps as possible. So that'll be 5 times x minus 2. And what do we have in the denominator? It looks like a 2x minus 1, doesn't it? No, plus 1. Something is squirrely here. I've made some dumb mistake somewhere here. Let's go back. H of f of x. There's my f of x. The h function says 5 over that plus 2. We multiply numerator and denominator by that. Okay, let's go back to 5x minus 10. This is a little more complicated than I thought. Let's do it this way. 5x over 2x plus 1 minus 10 over 2x plus 1. Is that going to help us any? Frankly, I don't see it does. Oh, I see what I did wrong. I wrote down my h wrong. I got it right here, but when I wrote it over here, yeah, the plus 2's up top. Sorry about that. That was totally crazy here. Oh, I'm racing too much, but okay. I knew that couldn't be right, okay, because it wasn't coming out right. Okay. All right, let's go back here. H of x is 5 over x plus 2 is out here, not underneath the denominator. Wrong, okay. So, I think we plugged it in properly this time. Okay. Second, yeah, here we just multiply x minus 2 here and x minus 2 here. Okay. Now, these go out and you get 5 times x minus 2 up here over 5 plus 2. The 5's go out, and you got x minus 2 plus 2. The 2's go out, and you're left ding, 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 ding with that. Sorry about that. I wrote down the h function, or f function, or no, h function incorrectly. All right, sorry about messing that up. But yes, we do get X in both cases. All right, good deal. There is a checkpoint there. Maybe I should go and do a checkpoint. Okay. All right. Let's move on to, we've already done this one. All right. Graphs of inverse functions. Because I lost too much time on that one, I think we're going to have to start there next time. Sorry about that, folks. We'll start here at the top of page 86. But also, we can do some homework exercises here. Let's do any of the odds 7 through 11. Do any of the odds, do either 13 or 15 or both. Okay. Do either 17 or 19. Oh, wait. That's catching the graph. Hold off. Just go through 15. 7 through 11, 13 or 15, or both. But we'll pick up the rest of it next time. Well, you can verify. So skip 17 and 19. I think you can go through and do any of the odds 21 to 31 also. Okay? And frankly, I think 33 and 35 may be something you can do. But if some of those higher numbers give you problems, hang on to them, we'll come back to them. Okay? Good deal. Any questions? Okay, catch this, folks. When we finish 1.9, which I'm going to hazard a guess may be Tuesday. That means we could have a test for Chapter 1 on Thursday. No later than the following Tuesday, but I'm guessing we could probably have it next Thursday, which is probably good to go and get it knocked out because we're getting relatively close to midterm. It'd be nice to have. You had a quiz and you had a chance to do a paper. Let's get a test done too. Okay? So it's either going to be Thursday, more likely Thursday next week. We'll probably have Chapter 1 test. Yeah, 10:45 to 12:30. I have to be in class at 12:30. I don't get out of here until 10:45.